Next example on Natani's method. Solve by Natani's method. Y in bracket 1 plus z square dx minus x 1 plus z square dy plus x square plus y square dz is equal to 0. This one is not now homogeneous differential equation. The previous example on the Natani's method, this example is what? This is the homogeneous differential equation, y square plus yz dx, zx plus z square, and therefore this is solvable by using two methods, that is Natani's method as well as the previous method, that is the method for homogeneous Pfaffian differential equation. But this example is now is not homogeneous. It may be solvable by using the method variable separable or three variable separable, one variable separable. So this is one variable separable. If we divide 1 plus z square, x square plus y square throughout, if we divide it by x square plus y square into 1 plus z square throughout, then what we have? Y dx minus x divided by x square plus y square, and then plus at this place we have 1 by 1 plus z square dz is equal to 0. That is, it is one variable separable. And 1 by 1 plus z square dz, its integration is tan inverse z. And the y dx minus x divided by x square plus y square is the derivative of what? Is the derivative of some function. That is the use the tricks. What are the tricks? That is x square. That is, we use the tricks. So already we solve this x. Yes, this is the x dy minus y dx divided by x square plus y square. Okay, x dy minus y dx divided by x square plus y square is the derivative of tan inverse y by x. That is, we have the solution. X dy minus y dx divided by x square plus y square. And if there is a plus sign, suppose x dy plus y dx divided by x square plus y square, then it is the derivative of 1/2 log x square plus y square. So use either this or this. So what is the example? The example is this is the example. Observe this example. So y dx minus x divided by x square plus y square. Then it is a derivative of tan inverse y by x or tan inverse x by y. That is the y by x or y x by y. So tan inverse y by x, derivative of the tan inverse y by x, y dx minus x divided by x square plus y square. And here 1 by 1 plus z square dz is the its integration is tan inverse z. Okay, is equal to 0, and therefore we have the answer tan inverse y by x plus tan inverse z is equal to constant of integration, suppose tan inverse c. So if we observe this example answer, then it is a tan inverse. Okay. So by using the Natani's method, this is the answer. This is the answer. Okay. Because tan inverse y by x minus tan inverse z, tan inverse y by x minus tan inverse z, if we simplify, we have the answer tan inverse y by x minus z divided by 1 into y by x into z by using this formula. So we have, I think, by using the both method, we have the same answer. So we'll, but here what is the method? We have to apply the Natani's method. Otherwise, this is this Pfaffian differential equation is one variable separable. This is of the one variable separable type. I think we have its answer in the one variable separable form. So see the one variable separable example on one variable separable. one variable separable. There are 4 types now to solve the Pfaffian differential equation. So first is what? All the 3 variables are separable, and the second one is what? Here, when one variable is separable. Okay, this is the type one variable separable. So observe these examples. So yes, x 1 plus z square dx plus y dy. Okay, our example is what? Y 1 plus z square dx. So this is of the type that is divided 1 plus z square into x square plus y square. We have this, and then x dx plus y divided by x square plus y square is the derivative of 1 half log x square plus y square. Therefore, its integration is this by using f dash x divided by fx rule, and 1 by 1 plus z square is tan inverse here. So the example is of this type, one variable separable. If you observe this example, okay, y 1 plus z square dx minus x 1 plus z square dy plus x square plus y square dz is equal to 0. So check first that it is integrable, then divide by 1 plus z square x square plus y square. So what we have? We have y dx minus x divided by x square plus y square. Okay, derivative of, and it is a derivative of tan inverse y by x by y, tan inverse x by y. So after dividing this, we have after dividing by this, we have this y divided by x square plus y square dx, then minus x square plus y square dy plus 1 by 1 plus z square dz is equal to 0. And then if we take x square plus y square as LCM, then what do we have? Y dx minus x dy. Y dx minus x dy, its simplification. And this y dx minus x divided by x square plus y square is derivative of tan inverse x by y. If we find the derivative of tan inverse x by y, then it is y dx minus x divided by x square plus y square. And 1 by 1 plus z square is the derivative of tan inverse z. And therefore, after integration, what do we have? Tan inverse x by y, its integration, tan inverse y x by y plus tan inverse z is equal to constant of integration. So this is the solution. And the same problem we have to solve this problem by using now Natani's method. That is, if the method is not compulsory, then we can solve the example by using any method. So this example is solvable by using the method of one variable separable, but here the method is we have to apply the method of Natani. We have to apply the Natani's method. So the question is what? By Natani's method, yes, by Natani's method, solve this example. Y in bracket 1 plus z square dx minus x 1 plus z square dy plus x square plus y square dz is equal to 0. This is one variable separable, actually type one variable separable, and we have its answer already by using one variable separable. Now we have to solve this example by using Natani's method. So first show that x bar dot curl x bar is 0. Therefore, the given differential equation is integrable. Then treating z as constant. Treat this z as a constant. This is the method, Natani's method. So first step is what? Treat z as constant. Therefore, dz is 0, and therefore equation 1 becomes y 1 plus z square dx minus x 1 plus z square dy is equal to 0, because dz is 0. And in this 1 plus z square is now constant, because z is constant. So treat that 1 plus z square, this z as a constant quantity. So separate the variables, shift these terms to RHS, and then dividing by shift this x to LHS, shift this y to RHS, and cancel 1 plus z square. Cancel this 1 plus z square. here cancel the 1 plus z square. No need of this 1 plus z square. And if it remaining as it is, then we have what we have seen. Then what we have, log x, 1 by x integration is log x, 1 by y integration log y, plus constant of integration log x minus log y. This 1 plus z square now shifted to RHS. 1 plus z square log c1. Then a log x minus log y is log x by y. Log x by y is this quantity, means we have log 1 plus z square log c1 is log c1 raised to 1 plus z square, and then x by y is c1 raised to 1 plus z square, and suppose this is another constant psi z. Okay, so cancel either 1 plus z square at this place. So we have this is psi z, c1, replace c1 by psi z, because this constant may contain function of it may be a function of z, because z is constant. So it is a method of it is a Natani's method. So after this, if you have to shift the function to RHS, that z function of z. So purely function of z. There is only one function of z, shift that, and then it is a psi z. Okay, so psi z is now constant of integration, because z is constant, and therefore the constant of integration may contains. If you cancel this 1 plus z square at this place, then we have the answer x by y is equal to c1, and then we write that is x by y as c2, as phi z, not c2, x by y as phi z. It is equation number 4. So in order to find psi z, we put x is equal to constant. Suppose alpha. In the discussion, general discussion, we substitute x as alpha. But here, in the particular examples, either substitute x is equal to 0 or 1. So put x is equal to 1. In the previous example, the value of x is 0. Here, the x is value of x is 0. But here is x is 1. Why? Because if we substitute x is equal to 0, then what are the equation number 4? We have if x is 0, then 0. We have psi z as a 0 by y, that is 0. That's why substitute x as 1, because we have to find the value of psi z. And therefore equation 4 and 1 becomes, equation 4 becomes 1 by y is equal to psi z. 1 by y is equal to psi z. If you substitute x is equal to 0, then we have psi z is 0. And if you substitute x is 1, then dx is 0. Dx is 0. So in order to find psi z, substitute x as 0 or 1 or 2. That depends on the example. And then equation 1 becomes, in the equation 1, substitute dx as 0 and x as 1. So we have minus 1 plus z square dy, 1 plus y square dz is equal to 0. Substitute x as 1. 1 minus 1 plus z square dy plus 1 plus y square dz is equal to 0. And this is equation number 5, 6. Minus 1 plus z square dy plus 1 plus y square dz is equal to 0. It is equation number 6. So equation number 5 is what? 1 by y psi z is equation number 5. And minus 1 plus z square dy plus 1 plus y square dz is equal to 0. This is equation obtained by substituting x1 and dx0 in equation number 1. And this is the equation number 4. In equation number 4, substitute x as 1. And then we have to solve this example number, equation number 6. It is a differential equation in 2 variables. So solve it by separating the variables or in another method. So dy divided by 1 plus y square, dz divided by 1 plus z square, by shifting the quantity to RHS, and then separate the variables, integrate it. So integration of 1 by 1 plus y square is tan inverse y. Then 1 by 1 plus z square is tan inverse z. After shifting LHS, we have minus tan inverse z is equal to tan inverse c. And then tan inverse y minus tan inverse z value is tan inverse z minus y divided by 1 plus z into y, or 1 tan inverse This, okay, z minus y divided by 1 plus z into y, tan inverse c2. And therefore we have z minus y. Take, check this rule, tan inverse a minus tan inverse b. I think it is tan inverse a minus b divided by 1 plus a into b. So if it is that form, then we write in the place of z minus y, write y minus z, tan inverse y minus z. If you write z minus y or y minus z, then we have absurd the sign at this place. Then cancel the tan inverse of both sides. Then this tan inverse C2 is the constant of integration. Tan inverse C2 is the constant of integration. First adjust the constant C1 and then add the constant C2. So here is the tan inverse C2 is constant of integration. Then cancel the tan inverse of both sides. We have z minus y or y minus z divided by 1 plus z into y is equal to C2. Then we have to eliminate y from this equation, and equation number 5. We have to eliminate y from this. So y is what? 1 by psi z. Substitute y as 1 by psi z in this example. Substitute y as 1 by psi z in this example, in this equation number 7. So what do we get? Z minus 1 by psi z, value of y, 1 plus z into 1 by psi z is equal to C2. And then after solving this equation, we have to find the value of psi z. So take psi z as a LCM of both sides. So psi z into psi z minus 1 divided by psi z, and here psi z plus z divided by psi z. Psi z get cancelled. So we have z into psi z minus 1 divided by psi z plus z is equal to C2. And then we have take z as common from this. We have psi z minus 1 by z, and here at this place we have 1 plus psi z by z is equal to C2. We have psi z minus 1 by z, z get cancelled, divided by 1 plus psi z by z is equal to C2. So separate, shift this RHS. Psi z minus 1 by z is equal to C2 in bracket 1 plus psi z by psi z. And so it is what? 1 after multiplying C2 plus C2 psi z by z. And then shift this quantity to LHS and take psi z as common. So 1 minus C2 by z is equal to C2 plus j. It is 1 by z plus 1 by z. And then psi z is C2 plus 1 by z divided by 1 minus C2 by z. Takes z as LCM. Z C2 plus 1, z minus C2, z get cancelled. And then psi z, put this psi z in equation number 4. We have to put this value in equation number 4. So we have x by y is equal to psi z is this z C2 z plus 1 divided by z minus C2. And this is the general solution of the given differential equation, or is called primitives of the given differential equation, or the integral surface of the given differential equation. Okay. So the question is what? Solve by Natani method, or find the primitives, or find the integral surface of the given differential Pfaffian differential equation by Natani's method. So next example on the same method, solve by Natani's method. So 2x dx plus 2y dy minus x square plus y square plus e raised to z dz is equal to 0. So first check x bar dot curl x bar 0, that is the given differential equation is integrable. Then take z as constant, or treat z as a constant, and therefore dz is equal to 0. So equation 1 becomes, substitute dz as 0. So 2x dx plus 2y dy is equal to 0. Equation number 2, solve this equation, dividing by 2, and then x square by 2 plus y square by 2 is equal to c1 dash, suppose, constant of integration. X square plus y square is 2 c1 dash, and then x square plus y square is equal to c1, equation number 3. And then this c1 may be function of z, because z is a constant function. And therefore we write x square plus y square is equal to psi z as equation number 4. By removing this c1, we write it is equal to psi z. Now we have to find the value of psi z. So in order to find psi z, substitute x as constant, x as 0. So in the previous example, x is 1. Now here we substitute x is 0, and therefore dx is 0. And therefore equation 4 and 1 becomes Equation 4 becomes this y square is equal to psi z, equation number 5. And equation 1 becomes, after substituting x at 0, we have dx is 0, this term is 0. So 2y dy minus 0 at this place. So minus in bracket y square plus e raised to z dz. Y square plus e raised to z dz is equal to 0, equation number 6. Now we have to find the solution of equation number 6. That is, we have to find the solution of equation number 6. And it is of the form m dx plus n dy is equal to 0. Actually, x and y are here, y and z. So it is m dy minus n dz is equal to 0. It is of this form. M dx plus n dy is equal to 0. And there are different methods to solve the Pfaffian differential equation in two variables. M dx plus n dy is equal to 0. In the previous year, K.J.Somaiya, there is a chapter that differential equation of first order and first degree. That is the differential equation. Different methods to solve the differential equation of the form m dx plus n dy is equal to 0. So how we can solve the differential equation m dx plus n dy is equal to 0? It is solvable by using the methods. If it is a variable separable, then solve by separating the variables. If it is not in the variable separable form, then there are another method, that is, it is either homogeneous type or it is a linear differential equation, or the given differential equation is of the type non-homogeneous, or the given differential equation is exact differential equation or Bernoulli differential equation. So these are the methods to solve the example. So here compare this equation with the m dy plus n dz is equal to 0. Obviously m and n are what? Now functions of y and z. So m is 2y, n is minus y square minus e raised to z. And if we check m by z and n by y, m is the coefficient of dy, so its derivative with respect to z, and the coefficient of n is the coefficient of dz, so its derivative with respect to y. These two are not equal. The derivative m by z is 0 and n by y is minus 2y. Okay, and therefore these two are not equal. So, but if we find m 1 by m n by y minus m by z, then it is what is equal to what? The derivative of the 1 by m is 1 by 2y, and n by y is 0 minus 2y. Okay, and then it is what? 1 by 2y minus 2y minus 0. Okay, m by y is 0. m by z is 0. So we have this, and this is equal to minus 1. That is the purely function of z. It is actually constant. It is purely function of z. And therefore we find the integrating factor I is equal to e raised to minus 1 minus phi z dz. So convert the theory of m dx plus n dy to m dy plus n dz is equal to 0. So actually the integrating factor is what? E raised to integration phi x dx or phi y dy. So here phi z dz. So phi z is minus 1, and then this is the general formula. Then integration of minus 1 is minus z. E raised to minus z is the integrating factor. So multiplying equation 6 by integrating factor, that is e raised to minus z. So what we have? 2y e raised to minus z, 2y e raised to minus z plus minus e raised to minus z multiplied by e raised to minus z. So we have y square e raised to minus z plus e raised to minus z into e raised to z dz is equal to 0. So 2y e raised to minus z dy minus this is e raised to minus z y square plus 1 dz, and this become exact differential equation now. After multiplying the integrating factor, this is one of the rule of finding integrating factor. So after multiplying by integrating factor, the given equation converted to exact differential equation. And now the solution of exact differential equation is what? Integration m dx plus terms in m independent of x dy is equal to 0. If the given differential equation is m dx plus n dy is equal to 0. But if the given differential equation is m dy plus n dz is equal to 0, then the formula is what? Integration m dy plus terms in m independent of y dz is equal to c1, and therefore m is 2y e raised to minus z. This is m minus plus integration. So terms in n independent of y. So this first term is depend on y, that e raised to minus z y square, and this minus 1. Now this minus 1, because there is minus sign, so minus 1, this term is only one term which does not depend on y. So minus 1 dz is equal to c1. So the terms in n independent of y is minus 1, and then its integration is y square. The integration of this e raised to minus z is now constant, and the integration of 2y is what? Y square 2, y square by 2 means y square, 2 get cancelled. E raised to minus z minus 1 integration is minus z is equal to c2. So this is equation number 7, and this is the solution of the equation number 6. Okay. So now eliminate y from 5 and 7. Eliminate y from 5 and 7. So value of y is root psi z from equation number 5. Substitute this root psi z in the equation number 7. So the value of we have y square. From this we have y square is what? C2 plus z divided by e raised to minus z, and substitute this y square as psi z. Y square as psi z. So we have C2 plus z divided by e raised to minus z is equal to psi z, or substitute y as root psi z, because from equation number 5 we have y is root psi z. So substitute y as root psi z. We have this, and then we have the value of psi z, and then substitute this value of psi z in equation number 4. We get the general solution, that is x square plus y square. What is the equation number 4? This is the x square plus y square is equal to psi z. So x square plus y square is equal to c2 plus z divided by e raised to minus z, and so this after simplification, e raised to minus z multiplied by e raised to minus z. So x square plus y square, e raised to right minus z, c2. Okay. If you shift the e raised to minus z to numerator, then it will become e raised to z. So x square plus y square is equal to e raised to z in bracket c2 plus z, and this is the general solution of the given differential equation. So there is some another problems on the Natani's method. So this is again one more solve problem on Natani's method. This problem, okay. X square z minus y cube dx plus 3x y square dy plus x cube dz is equal to 0. Again, this is the homogeneous Pfaffian differential equation of degree 3. So it is solvable by using the method of homogeneous Pfaffian differential equation. That is, substitute y as vx and z as wx. So, but here we have to solve this example by using Natani's method. So check whether x bar dot curl x bar is 0 first. Then treat z as constant. Therefore dz is 0. So after substituting dz is 0, we have this, and we have to solve this equation. So m is this, n is this after comparing. So da by m by da by y is this minus 3y square, and da by n by da by x is what? 3y square. These two are not equal, but 1 by n da by m by da by y minus 1 by minus da by n by da by x is what? We have this as minus 2 by x as a function of x, purely function of x. And so integrating factor is what? E raised to integration pi x dx. So e raised to integration minus 2 by x dx, that is e raised to minus 2 log x. So e raised to log x raised to minus 2, x raised to minus 2, e raised to log x raised to minus 2 is x raised to minus 2, that is 1 by x square. So 1 by x square is the integrating factor. So multiplying the equation, this equation number 2 by 1 by x square, multiplying by 1 by x square. So we have this z minus y cube by x square dx plus y cube by x square dx plus 3y square by x, 3y square by x. Okay, by multiplying by 1 by x square, we have this, and then it is a now exact differential equation, and we have to find its solution. Integration m dx plus terms in n independent of x, terms in n independent of x, dy is equal to 0. So this is the formula, integration, and this is z minus y cube by x square dx plus terms in n independent of x is 0, there is no term, so write 0 dy is equal to c1, And now integration with respect to x, z is now constant. So its integration zx minus y square by x square, integration y cube by x square. Y cube is constant, and the integration of minus 1 by x square is plus 1 by x is equal to c1. So we have two, not two, zx plus y cube by x is equal to psi z. Suppose leave constant psi z. This is equation number 4. Then in order to find psi z, put x is equal to 1 in equation number 4 and 1. So x is 1, therefore dx is 0. Therefore equation 4 becomes this equation z plus y cube by 1, that is y cube, is equal to psi z equation number 5, and equation number 1 becomes 3y square dy plus dz is equal to 0. Equation number 6. Now we have to find the solution of equation number 6. So it is y cube, the integration of this 3y square is what? 3y cube by 3. So it is y cube plus dz integration is z is equal to c2, new constant. And then we have to eliminate y from 5 and 7. So what you have to eliminate y from 5 and 7. So subtracting these two, yes, we have directly what we have, psi, yes, z plus y cube is psi z, z cube plus yz. So right, substitute z plus y cube as psi z. So we have psi z is equal to c2. Or subtracting these two equations, we have psi z is equal to c2. Then put psi z as c2 in equation number 4, we get the general solution, that is right in the psi z as c2. So zx plus y cube by x c2 is, which is the general solution of the given differential equation. So these are some examples on Natani's method for homework or assignment. Solve these examples by using Natani's method. Their solutions are given. Yeah. 5, 6, 7, 8, 9. So these are some examples. This is not integrable. I think this is not integrable. This is not integrable. So don't solve these examples. So their solutions are given. So try to solve these examples by using Natani's method. There may be some mistake in these problems. So solve at least three problems by Natani's method. So the next method is the reduction to ordinary differential equation. So we will see this method in the next lecture, reduction to ordinary differential equation.